Before we start with today's lecture, an announcement from the, the teaching staff. It seems many people didn't realize that there's a queue for office hours. If you want to get in the queue, you should go to that website. Or you can go to cs170.org. There's a link at the top right. And I was also asked to tell you that the TAs prioritize conceptual questions over homework questions. So people who have conceptual questions jump the queue before homework question people. Okay, good. So last time we talked about the efficiency of arithmetic, namely addition and multiplication. And we saw that there's a faster algorithm for multiplication than the standard algorithm we all learned in grade school. Today, what's on the menu for today? We're going to talk about computing Fibonacci numbers. And I'm going to describe 4 different algorithms, and each one is seemingly going to be exponentially faster than the previous one. Okay, down to constant time. Okay, maybe. And then I'm going to talk about a little more about asymptotic notation. I've been kind of throwing it around without properly defining it. So that's like big O, theta, big omega, etc. You'll get more practice with that on the homework and discussion. And then I'll talk about divide and conquer, more divide and conquer. So I mentioned that this approach of taking your input, splitting into pieces, recursively solving the pieces, then putting it back together, that approach is known as divide and conquer. That's what we did in Karatsuba's algorithm. That's a more general approach to algorithm design. And we're going to see at the end of this lecture, as well as into next lecture and even the lecture after, more examples of using divide and conquer to get fast algorithms. So more divide and conquer. As well as a general way to analyze the recurrences. Let's say I break into A pieces, each which is only is a factor B smaller, and combining them takes n to the D work. What's my overall running time going to be? There's something called the master theorem, which we'll discuss, for analyzing recurrences. So last time I mentioned that the number system that's the most popular today was invented in India, popularized by a man named Al-Khwarizmi from Persia, and then even further popularized further westward by Fibonacci. Okay, so I guess that's one of Fibonacci's claims to fame is popularizing the numerical system that we all use today. Although he didn't invent it, he was just a popularizer. He was a promoter. Okay. But we also know, I guess, from previous classes, maybe 61A, the Fibonacci sequence, right? So what is the Fibonacci sequence? It starts off with 0 and then 1, and then the next number is always the sum of the previous 2 numbers. So 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, etc. It's an infinite sequence. And to be honest with you, it's not the most important sequence in the world. Okay, computer scientists just like to use it in the classroom setting because you can use it to teach a lot of different concepts, like recursion, for example. Okay. I'm going to use it to illustrate kind of some mistakes when analyzing kind of complexity of arithmetic operations and what you get when you analyze things correctly. So I want to show you 4 different algorithms for this problem. Algorithm 1 is just recursion. I'll call this, by the way, I'll index from 0. This is the 0th Fibonacci number. This is the first. This is the second, etc. So fib n I'll say if n is less than or equal to 1, return n. Okay, so that works for 0 and 1. Otherwise, return fib n minus 1 plus fib n minus 2. And analyzing runtime, I'm going to analyze, the way I'm going to do it is, I'm just going to count arithmetic operations. So we'll count flops, which are just floating point operations. Basically, for us, it's just going to be multiplications and additions. So let T of n be the number of arithmetic operations, or flops, I need to compute fib n, the n Fibonacci number, using this algorithm. Well, if I'm in the base case, I don't need anything, right? Let's say 0. I know the answer. I don't need to do any floating point operations. Otherwise, I'm going to do something like, well, T of n minus 1 to compute fib of n minus 1 plus T of n minus 2 to compute fib of n minus 2. And then I do one more because I then add them together. That's one more floating point operation. And this thing looks a whole lot, it's not exactly the same, but it looks a whole lot like the Fibonacci recursion again. Okay. So let me just try to convince you that this thing is large. Let's look at the Fibonacci sequence. The nth Fibonacci number is the n minus first plus the n minus second. And the Fibonacci numbers strictly increase, right? Like the nth Fibonacci number is bigger than the n minus first, which is bigger than the n minus second, et cetera. If you wanted to be super pedantic, which I don't encourage in this class to be super pedantic, but if you want to be super pedantic, formally, how would you prove that the Fibonacci numbers are increasing? What's the one-word proof? Or the one-word thing that would start your proof? Induction. You do induction on n. Okay? But we're not going to be super pedantic. You can prove this if you want by induction. These numbers increase, which means f of n minus 1 is at least f of n minus 2. So this is at least 2 times fn minus 2. Right? And again, the thing I'm about to say next, so okay, we can just keep iterating. So this is at least 2 times 2 times f of n minus 4, which is at least 2 times 2 times 2 times f of n minus 6, et cetera, right? So this thing is at least something like 2 to the n over 2. Because when I get down to f1 or f0, I get down to a constant. Or f1 or f2, I get down to a constant. Maybe I'm off by 1. Maybe it's n over 2 minus 1. I don't really care. Okay. But what this tells me is that the nth Fibonacci number is exponentially large in n. Right? It's at least square root of 2 to the n. It's at least 2 to the n over 2. And a very similar argument basically says the same thing for this recurrence. Okay. So this would be like some exponential. So this is like, So this is basically exponential in n, right? So at least something like 2 to the 0.5 n flops. Okay. So that's algorithm 1. Let's do algorithm 2, which is iteration. And here what we're going to do is we're going to say, look, okay, so here's now faster fib. Again, I'll say if n is less than or equal to 1, return n. Otherwise, I'll say A is 0, B is 1. So basically, A and B are keeping track of the last two Fibonacci numbers. And for let's say I equals 2 to n, what I want to do now is update. So I'm moving forward one. So the new A is what B was, and the new B is the sum of them. So let's say temp is A plus B. A gets B, and B gets temp. And then down here I return B. Okay. This, by the way, I mean, it looks like a very simple algorithm. It's actually a special case of, or it's an instantiation of a more general algorithmic technique called dynamic programming. Actually, it's dynamic programming with a memory optimization. You might not know what that means now, but you will in a few weeks. Okay. And how many floating point operations are there here? Well, I go through this loop n minus 1 times, and each one I do an addition. So there are like n minus 1 flops here. An exponential improvement, right? From exponential in some constant times n to linear in n. Let's get yet another exponential improvement. Who here has no idea what a matrix is? Everyone is fine? Okay. So I can define a matrix as follows. 1, 1, 1, 0. And then I can define a vector as follows. Let's say this is F1 and this is F0. Okay. And I can compute this matrix vector product. And if anyone was shy and didn't feel like maybe admitting, oh yeah, so everyone's familiar with, let's say, matrix vector multiplication. Anyone not familiar with matrix vector multiplication? Okay. I'm going to do the same thing even if you said, no matter what you answer, because I want to make sure that no one's shy and maybe is not willing to admit that they don't remember. But matrix vector multiplication, basically, if you multiply, right, an A by B matrix by a B by C matrix, here C is 1, then the output matrix is A by C, and each entry is the dot product of the corresponding row and column, in the row in this matrix and the column here. So this is a 2 by 2, this is a 2 by 1, so this is 2 by 1. And this entry, this is the first row, first column. So I get it by dot producting the first row and the first column. And the dot product there is F1 plus F0. Right, so this is, let's say, F1 plus F0. And then this is the second row, first column. So I dot product the second row with the first column. And then I just get F1. And this is also known as F2, F1, right? Because F0 plus F1 is F2. And more generally, if I call this matrix, let's call this matrix capital A. If I look at A raised to the nth power, meaning apply A over and over again, to the vector F1, F0, this is going to be f of n plus 1, f of n. Again, if you wanted to formally prove that, you would use induction. Okay. Okay, so now one thing to know about matrix product is that it's associative, right? What does this mean? So let's call this vector v. So this is like A times A times A times A times v. It's associative, which means I can choose, I can parenthesize this however I want and get the same answer. So I could do like, let me first do A times v. That's going to give me a new vector. And then let me do A times that vector. That's going to give me a new vector. But I don't have to do it that way. I could parenthesize it so that I get the product of all the A's first, and then apply that to v. So let's figure out how are we going to quickly get A to the n. Okay, so we could do A times A. That takes a constant number of flops. It's a 2 by 2 matrix, right? So multiplying a 2 by 2 matrix by a 2 by 2 matrix takes some constant number of flops. So A by A is a constant number of flops, times A again is a constant number of flops, times A again is a constant number of flops. So they're entities, so it's basically O of n flops, right? And then finally we can apply that to V, and that's another constant number of flops, right? Because it's again 2 by 2 matrix with a two-dimensional vector. So overall, this could give us an O of n flop algorithm, but we already have an O of n flop algorithm. So we can do even better using a technique known as fast exponentiation by repeated squaring. Okay? So let me describe to you how that works. So forget about matrices. Let's just think about integers, right? Suppose I wanted to know 9 to the 71st power. Right? Well, I can compute a bunch of things. I can compute 9 to the 0. Well, I don't really need 9 to the 0. 9 to the 1. Once I have 9 to the 1, which is 9, I can square it. That's one flop to square it. That gives me 9 squared. Now I have 9 squared. One more flop. I can square it, multiply it by itself. That gives me 9 to the 4th. I can square that and get 9 to the 8th, 9 to the 16th, 9 to the 32, and then 9 to the 64. Right? How many flops did I need to do this? Basically, going from one to the next is just one multiplication. So overall, it's like how many powers of 2 do I need before I reach 71? Basically, log base 2 of 71. So in log base 2 of 71, or the floor of that, maybe the ceiling of that, I can get all the powers that look like 9 to some power of 2. Okay. Now what I can do is I can write 71 in binary. What is 71 in binary? It's 64 plus 7. 7 is 4 plus 2 plus 1. So this is 64 plus 4 plus 2 plus 1. So in binary, that's 64. I don't have 32. I don't have 16. I don't have 8. I do have 4. I do have 2. I do have 1. Which means I'll take this one. I'll take this one, and this one. And then I'll multiply them together. Right? So I did about log n, log base 2 of n flop. Well, let's say, this is more generally, this is n, right? So this is basically, this is my n, 9 to the n, 9 to the 71. I did about log base 2 of n flops in order to get all these powers of 2 as exponents. And then I do another, at most, log of n flops to multiply the relevant ones together. So altogether, I'm doing at most something like 2 log n flops, 2 log base 2 of n flops. Right? There's nothing special about 9 being an integer. 9 could have been a matrix, right? So I calculate basically that matrix A raised to various powers of 2, and then I multiply the relevant ones together. Each time I do a matrix-matrix multiplication, it's a 2 by 2 matrix times some other 2 by 2 matrix, which again is O of 1 flops, a constant number of flops. So altogether, this is going to give me, this approach, if done with repeated, by the way, this technique is known as repeated squaring. Just some jargon as to what people usually call this trick. I can get O of log n flops. Okay, so we went down from exponential in n to log n, and now we're going to do constant. Okay, so now maybe some people will say they don't know. Everyone take a linear algebra class yet? Who has not taken linear algebra? Okay, some people have not. Okay. Who doesn't know about finding eigenvectors and eigenvalues? Most people know, but not everyone. So we have this matrix A. Well, we said, okay, this is what we said, right? We said that A to the n, so this is algorithm 4 now. And this is, I'll just call this like constant time. We want to compute A to the n times V. Okay? Now, suppose we could write A, we could get the eigenvalue decomposition, and we could write A as Q lambda Q transpose. Okay? Where Q is an orthogonal, what's called orthogonal matrix. That is, Q transpose Q is the identity matrix. The identity matrix is just 1, 1, 0, 0. Right? And lambda is diagonal. These are the eigenvalues. If I could get this decomposition, then let's think. So I'm trying to compute A to the n times V. What's A squared? A squared is Q lambda Q transpose Q lambda Q transpose, right? But Q transpose Q is the identity. So it kind of goes away. And lambda times lambda, lambda squared, these entries just get squared. So this would just be Q lambda squared Q transpose. More generally, A to the n is just Q lambda to the n Q transpose. Okay, so this isn't going to be exactly constant time. Actually, it's more like log n, but you'll see what I'm going to say. So we just need to find this kind of decomposition. And then, okay, I mean, once we find this decomposition, like lambda 1 and lambda 2, they're just going to be some numbers, right? There's no n here. Like A is a fixed matrix. A is 1, 1, 1, 0, right? What's kind of the eigenvector decomposition of this matrix 1, 1, 1, 0? It's just something that doesn't change with n. It's whatever it is. And you can calculate it. If you don't know how to calculate it, that's fine. I'll just tell you what it is. So let's define some numbers. Phi is 1 plus the square root of 5 over 2. Psi is 1 minus the square root of 5 over 2. Then it turns out that I can write lambda 1 is basically phi, lambda 2 is psi, and then this matrix Q looks like square root of phi minus the square root of minus psi, 0, and then here I have square root of minus psi, square root of phi. Oh, no, that's not 0. By square root of psi, square root of psi. Okay, so I think did I typo this? Just give me a sec. This is something that I don't know by heart. This is some computation. Here we go. I'll just write it not in terms of psi, because I have it written down in terms of what it actually is, in terms of square root of 5, etc. Oh, no, here we go. 1 plus, okay, so yeah, so basically it's phi and psi down here. No. Square root 1 plus square root of 5 over 2. So this is basically square root of phi. Minus square root of minus psi. Square root of minus psi. And square root of phi. Times 1 over the fourth root of 5. Okay. It is what it is, okay? It's something weird. And if once you see this, or once you know this, and you plug it into that, a to the n is equal to q lambda to the n times q transpose, which we're then applying to the original vector, which is 1, 0. F1 of 0 is 1, 0. What you end up being able to prove is that the n Fibonacci number is something like 1 over root 5 times phi to the n minus psi to the n. Okay. So it's like some exact formula. The form of this is not all that important. I just wanted to say that there is some exact formula for the n Fibonacci number, and this is how you get it. It does involve powering. Okay, so maybe I lied. It's not really constant time. And it does involve square roots, which is that a basic floating point operation? I don't know. But the running time, I don't know. But it's some exact formula. Okay. So let's just even if we ignore this algorithm that has square roots, let's just look at the first three algorithms. I said the runtimes are exponential in n, linear in n, and logarithmic in n. Okay? Does everyone feel comfortable? Everyone feels like they understand that? That makes sense? Everyone feel like some part of that didn't make sense? Okay. So why not? Multiplying 2 by 2 matrices? Yeah. A 2 by 2 matrix times a 2 by 2 matrix is constant time. Constant time, not O of n time. But there were n of them, right? If I had done it in sequence, multiplying these two takes constant time, and then there's another one that's another constant. So I do that n times, that's O of n time. But if I do it using repeated squaring, I only need log n flops. So the truth is that, yes, algorithm 1 does take exponential flops, algorithm 2 does take linear flops, and algorithm 3 does take log n flops. But this is an example where flops is not the same as time, right? And why not? Because these numbers, actually multiplying two numbers doesn't take constant time. It depends on how many digits are in the numbers, right? And adding two numbers doesn't take constant time either. It depends on how many digits are in the numbers, right? We saw that in lecture 1. Adding two d-digit numbers takes d time. Multiplying two d-digit numbers takes d squared time, or maybe d to the log base 2 of 3 if you use Karatsuba, or maybe d log d if you use the fanciest thing that came out a year ago. Okay, but it's not constant time. So let's try and understand what the run times of these algorithms actually are. The first thing that I'll tell you is, okay, so this tells us that the n Fibonacci number is at least exponential in n. Okay? It turns out that the n Fibonacci number is also at most exponential in n. And I guess the easy way to see that is, well, we saw what the exact formula is, right? The n Fibonacci number is exactly that. And phi is some number. It's like 1 plus square root 5 over 2. So the n Fibonacci number is certainly at most, you can even drop the psi to the n. The n Fibonacci number is at most phi to the n, and it's at least root 2 to the n. Phi is just some number. It doesn't depend on n. Either way, what we see is that the n Fibonacci number is basically growing exponentially with n. Okay? So if the n Fibonacci number is growing exponentially with n, it's like roughly 2 to the cn for some constant c. How many digits is the n Fibonacci number? Log of that, right? Which is linear in n. Right? So we see the n Fibonacci number, Fn, is some exponential in c times n, which implies it's basically theta of, and theta is like, big O is like at most, I said this already, big O is like at most roughly, and theta is like roughly equal to, up to a constant factor. It's theta of n digits. Just log of that. Okay. So now let's try to understand the real runtimes of algorithms 1, 2, and 3. So runtimes. So let's see, let's do this. Here I have which algorithm it is. Here I have the flops. And here I have the actual runtime. So we have the recursive algorithm. We have the iterative algorithm. And then we have the matrix mult, the matrix powering. And this was some exponential number of flops. This was linear number of flops. And this was log n number of flops, up to a constant. So each one of these flops is on numbers that are like roughly n digits long. So I mean, it's still exponential number of things. Each one is taking some polynomial in n. I mean, it's basically some exponential in some constant times n times some smaller stuff, right? Stuff that's only polynomial. Small relative to exponential anyway. It's still an exponential time algorithm. So let's not be too pedantic about understanding exactly the runtime. It's exponential. How about the iterative algorithm? Okay. So that iterative algorithm over there, each one of these numbers you're adding together is at most roughly n digits long. You're doing roughly n additions, so it's n squared. It's at most n squared. How about matrix powering? So here you have to be a little careful. Okay? So it seems like it's better, right? It's log n flops. Those flops are coming from matrix-matrix multiplication, right? When you multiply two matrices together, you have to multiply numbers together. The entries have to get multiplied together and then added up. These numbers are related to the Fibonacci numbers. They're also growing like n digits long, right? You multiply them together, that's n squared. And you're doing log n flops. So your overall runtime is n squared log n. That's even worse than the simple iterative algorithm, right? Okay. So it's certainly at most some constant times n squared log n. Yeah. Yeah, okay, so if you use that, yes. But if you did it using, yes. So it depends which matrix multiplication algorithm you use, right? If you just used the one you didn't know before Tuesday, if you didn't use Karatsuba and the more advanced stuff, if you use the n squared algorithm, you would get maybe n squared log n. It's actually a little bit better than that, and the reason is, as you're doing the exponentiation of the matrix, the numbers in the powers of A get bigger and bigger. Initially, the numbers are only 1 digit long, right? And then when you take it to like the 10th power, the numbers roughly get proportional to 10 digits long. So yes, all the digits along the way, all the numbers along the way are at most n digits, but they're not all n digits. They're gradually getting to be up to n digits. So if you're a little bit more careful about your analysis, you can actually say that kind of you have some geometric series that's dominated by n squared. So you can actually do a little bit better and say, actually, you don't need the log n, this is n squared. Right? So basically what I'm saying there is, so in the matrix mults approach, in the powering approach, when you square a to the k, right? So you start with a to the 1, then you have a squared, then you have a to the 4th, etc. So let's say you have a to the k and you square it. I claim the entries in a to the k are roughly k digits long. Okay? The entries are at most ck digits long. So multiplying them together takes time proportional to k squared. And as you're doing repeated squaring, k is basically, k keeps doubling each time, right? You start with 1, then 2, then 4, etc. Right? The powers are 1, then 2, then 4, then 8, etc. So up to log n. Up to 2 to the log n. So the total time is something like, at most, c times kind of 1 squared to multiply these two one-digit numbers, plus 2 squared, plus 4 squared, plus plus n squared. All of these along the way are not n digits long. That's what I'm trying to say. The intermediate results are shorter numbers. And this sum turns out to be O of n squared. I'm not going to prove that right now. But you don't have to pay, even though there are log n terms here, since they're decreasing in size, kind of it's mostly dominated by the last one. So that's why you don't actually pay the log n. That's why you get n squared. But that's if you use the grade school multiplication algorithm. As you said, if you don't use the grade school multiplication algorithm, if you use an algorithm that can multiply two n-digit numbers in, say, m of n time, m of n is some function, like n to the log base 2 of 3 or n. And you know m of n is at least n, right? Because you can't multiply faster than n time. You can actually get this down to basically m of n time, where m of n is the runtime to multiply two n-digit numbers. Okay? But notice, unless you used that, unless you did something fancy like Karatsuba, just reducing the number of flops is not enough to actually improve the runtime. Does that make sense? Yeah.
Doesn't that depend on how you define runtime? Like if I'm running on a machine that only has fixed arithmetic, then the best I can do is just multiply two 64-bit numbers. That's going to take one cycle, right? So the flops would be more proportional to the actual runtime.
You said, doesn't it depend on how I implement the algorithm on my machine? Is that what you're saying?
Yeah, if I can only do like 64-bit, floating point operations per cycle,
Yeah.
then the thing that stays in time is the cycle, and so my flops would be directly proportional to it.
Okay, so you're saying, doesn't it depend on whether or not my machine supports 1-bit operations per cycle, or 32-bit floating point operations, or 64-bit floating operations? I mean, so my machine, the way to think about all of this is, my machine is a fixed machine, okay, that somehow, okay, so for the sake of this class, the machine has kind of access to an arbitrary amount of storage, okay? Maybe even if the machine itself doesn't have a big enough hard drive, it can go and talk to some other, medium of storage somewhere else. But it has access to an infinite amount of storage. But kind of the architecture of the machine, the CPU is a fixed thing, right? So the CPU does not depend on n, right? The instructions that are supported by the architecture do not depend on n. So yes, whoever built this CPU might have built it so that it supports multiplication, on 64-bit ints. Okay, but whatever, however big that word size is, 32-bit, 64 bits, etc., it's going to allow me to write my numbers in a larger base and shrink n, right? So instead of writing base 10, if I write base 100, it means basically I shrunk n by 2. But I'm not going to change n by more than a constant factor doing that, right? By changing the base, I can only change n by a constant factor, which means the n squared is still now, instead of n squared, it's n over 2 squared. But it's still proportional to n squared. I'm still going to get proportional to m to the n. I'm still going to get something that's exponential in n, maybe with a different constant, because n changed by a constant. Okay, does that answer your question? Okay, great. So that's all I wanted to say about Fibonacci. And then now I want to, before I give you another example of divide and conquer, I've been throwing big O and big omega and theta around without formally defining them. I want to define them, and then I'm going to do a little bit more divide and conquer. So let's do that. So asymptotic notation. What I'm going to talk about is notation that lets you compare two functions. And you should think of these functions as representing, say, the running time of an algorithm. So f of n is like how many steps, what's the worst case for the number of steps my algorithm takes on inputs of size n. So I have one algorithm that runs in f of n time. I have another algorithm that runs in g of n time. And I want to know which algorithm is better. Okay, that's often in this class where we're going to be using asymptotic notation. We're going to be using it for that purpose. So let's say f and g are functions mapping positive integers to positive integers, like n to the number of steps on inputs of size n. This is positive integers. There's a more general definition that applies to functions that could have arbitrary real output, and they're even negative, but it's not super relevant for the class. Okay, but I think you might get some practice with that in discussion anyway. So how do I compare them? So f, let's say f equals big O of g. This is pronounced big O. Actually, let me write it here. So big O. F is big O of g if there exists a constant such that for all n, f of n is at most some constant times g of n. So you can think of big O as a less than or equal to. F does not grow faster than g, up to some constant, c. And then there is big omega. Oh, actually, let's do little o next. Little o f is equal to little o of g if the limit as n goes to infinity of f of n over g of n is 0. Yeah.
So for the big O one, you can also use the limit definition. Can you use that in the homework or the exam?
Okay, so you said for big O you can use the limit definition. Can you use that in exams or whatever? So actually, that definition is wrong. Okay. Well, okay, so it's almost right, you cannot define big O in terms of limits. You can define big O in terms of the lim soup. Okay, maybe that's what you meant. Okay, yeah. So that's an equivalent definition. And maybe I'll do so for everyone else, for everyone's benefit, I'll show you an example just where you can't, if you try to define, let's say that you said f is big O of g, if the limit of f over g is if there exists a c, such that the limit of f over g is at most c. Or if you just say, like, it's less than infinity. If the limit of f over g is less than infinity. That would be an incorrect definition for big O, and I'll show you an example. And then there's big omega. F is big omega of g if basically g is big O of f. So you can just replace that less than or equal to with greater than or equal to if you want. And then little omega f is little omega of g if g is, again, little O of f. Okay. And what's theta? F is theta of g if both f is O of g and f is omega of g. Okay? So let me, I'm going to do a few examples, but before I do that, I want to write down kind of a little chart to help you, have an analogy in mind for what these things mean. So, analogies. If I see, there's what I say, big O, little o, big omega, little omega, theta. Big O is sort of like less than or equal to. Little o is sort of like strictly less than. Big omega is like greater than or equal to. Little omega is like strictly greater than. And theta is like equality. So these are the analogies to keep in mind, right? If I say that this algorithm's runtime is big O of the other ones, it means it's less than or equal to the other one's runtime, up to a constant, right? Similarly, if I say it's little o, it means this algorithm is strictly better. Its runtime is strictly better than the other one. Little omega means it's strictly worse. Capital omega means it's at least as slow as the other one. And theta means they have basically the same runtime up to a constant factor. Okay? Now, just in terms of like how can you see whether or not something is big O, let's say that, f of n examples, f of n is 3n cubed plus n squared plus log n. And let's say g of n is just n cubed. Well, we could look at, we could look at the limit. Let's look at the limit of f of n, which is 3n cubed plus n squared plus log n over n cubed. Let's look at this limit as n goes to infinity. It's equal to 3, right? Which means for n very, very large, this function is only, let's say I put n cubed in the Yeah, this function is at, for n very, very large, it's only roughly 3 times bigger than this function. So if n is large enough, it's definitely at most 4 times larger than this function. Right? So there's some n beyond which it's only 4 times larger. And for all the n's below that threshold, okay, the ratio is at most something, because there are only finitely many n's below that threshold. Right? So kind of the max that the ratio could ever be is the max of 4 and whatever it is below that threshold, if that makes sense. Okay. Maybe I'll write that down. I see a couple of confused faces, so maybe I'll write that down a little more explicitly. So this implies that there exists some very large number n, I don't know what that number is, maybe it's not that large, such that for all n bigger than or equal to capital N, f of n over g of n is at most 4. Right? If the limit is 3, that means the ratio is getting closer and closer to 3, and it's converging to 3. That means at some point it has to be below 4. So what that means... What that means is, if I look at like all the integers, let's say n is equal to 1, 2, 3, 4, up to that threshold capital N, and then I have n plus 1, n plus 2, up to like forever. If I look at the ratio f over g, f of n over g of n, what is it for n equals 1? Oh, it's something. Let's just write down what that something is. It's a1. What is it for 2? It's some other number. It's a2. What is it for 3? It's some other number. Down to, finally when I get to capital N, I know that it's at most 4. Right? And I know that this is also at most 4. I know that this ratio is also at most 4. From then on, forever, it's at most 4. This means that for all n that are at least 1, not just bigger than capital N, but for all n, f of n over g of n is at most c, where c is basically the max of a finite collection of numbers, a1, a2, up to a capital N minus 1, and 4. So this is my c, okay? which matches basically that definition that I gave for big O. So if you are able to prove that the limit is something that's finite, that does imply big O. But it's not, big O is not equivalent to the limit being finite. And the reason is just a technicality. The reason is the limit might not exist. Right? So suppose you have a function, suppose instead I had another function h of n, which is equal to 2n cubed if n is odd, and n cubed if n is even. H of n is big O of n cubed, right? Because I could put the constant 2 over there. But the limit of h of n divided by n cubed is not, it doesn't exist. Because the ratio doesn't converge to anything. It keeps bouncing back between 2 and 1. Okay? So just be careful with that. There is something called the lim sup. I'm not going to go into it. Look it up if you want. You can define big O in terms of something called the lim sup. But you can't define it in terms of limit. Lim sup, yeah, if you want to look it up. Lim sup. Limit superior. Okay. But anyway, that definition is suffices. Okay? So you'll have, I'm not going to spend too much time on this. You'll have more practice with asymptotic notation on your homework and in discussions. Questions? Okay. So I want to do one more example of divide and conquer. But before I do that, you remember last time when we covered Karatsuba's algorithm, what did we say with Karatsuba's algorithm? We said that we had these two integers we wanted to multiply. We broke them each into two pieces, right? We recursively did 3 multiplications. Then we combined them in linear time. We had some recurrence that said t of n is at most 3 times t of n over 2 plus some constant times n. And then we ended up saying that this was big O of n to the log base 2 of 3. Right? Does that sound familiar? That was Tuesday. So, more generally, what if I have some problem where I divide into pieces that are not a factor of 2 smaller, but a factor of b smaller? Let me just parameterize everything. And then I need to do a recursive calls. And then putting it together takes n to the d time. What runtime would I get? Okay. And we're going to write a very general theorem that basically always gives the right answer. And then we're going to cover one more example of divide and conquer. So what about t of n is at most a times t of n over b plus some constant times n to the d? What would we get then? So we're just going to analyze it the same way we analyze Karatsuba, which is we're going to draw the recursion tree. We're going to add up for each level how much work did we do on that level, and then we're going to sum that all up and see what we get. Okay. So at the root, we do c times n to the d work. And then that makes a recursive calls. Each one of those children does, what's n now? N is n over b. So c times n over b to the d work. And then each one of these children makes a recursive calls. And then this child does c times, what's n now? It's n over b squared, right? N over b, and then we divide it by b again. N over b squared to the d. So let's see what the time per level is. Here it's c times n to the d at the root level. There's only one node. And then here, after I do the recursive calls, the amount of time it takes to put everything together, well, this is, each one is giving me an n to the d, and there are a of them. So they're a times n to the d over b to the d times c. So it's c times a over b to the d times n to the d. Right? Let me just do one more level. Okay, so it's c times, again I have n to the d, so I'm going to have n to the d. How many nodes do I have? Well, I had a children, then each one of those had a children, so I have a squared nodes. And each one is dividing by b to the 2d, which is the same thing as b to the d squared. So this is a over b to the d squared. So the general thing is, right, if I go down k levels, c times a over b to the d to the k times n to the d. That's at the kth level. So, okay. So what's the total time? So if you remember from last time, 1 plus p squared plus plus p to the k is equal to, well, there are cases. If p is 1, it's just k plus 1. K plus 1 if p is 1. If p is not 1, it's p to the k plus 1 minus 1 over p minus 1, if p is not equal to 1. This is what we saw last time. Right? This formula doesn't work when p is 1 because there's a part, you can't divide by 0, basically. The formula breaks down. But when p is 1, it's easy to see that there are k plus 1 terms here. They're all 1. Okay, so now let's look at, we have now our time, our total time, is all of them have a c times n to the d. And then we have 1 plus a over b to the d plus a over b to the d squared plus plus a over b to the d to the k. What's k? How many levels of recursion do I have before I'm done? Log base b of n, right? Because I'm done. I didn't write it, but let's say my base case is 1, n is a constant, and it takes constant time. I'm done when, say, n over b to the d, to the k, sorry, is at most 1, which implies I'm done when k is at least log base b of n. Right? So k is log base b of n. Okay, so now there are cases for what this is. And one case is going to be when p is 1. Right? So what is this thing? When p is 1, that basically means a over b to the d is 1. If a over b to the d is 1, all these terms are 1. How many terms are there? Log base b of n. Okay? So this is O of, and there's n to the d here, n to the d times log n if a is equal to b to the d. That's one case. Now two other cases. Let's look differently at, well, okay, let's just write it down now. Let's write down over here. So we have a over b to the d actually, let me give myself a little more space. So that's, in the other case, what I have is c times n to the d times p to the k plus 1 minus 1 over p minus 1. What's p to the k plus 1? It's a over b to the d to the log base b of n, right? Plus 1 minus 1 over a over b to the d minus 1. Now, let's again, I like this trick of, right, a is equal to b to the log base b of a. So this is equal to c times n to the d times, I have a plus 1 here, so that gives me a factor of a over b to the d. And then a is b to the log base b of a raised to the log base b of n over b to the log base b of n to the d minus 1 over a over b to the d minus 1. Okay. Right here, b to the d to the log n is the same as b to the log n to the d. B to the log base b of n is n. And then I have n to the d. N to the d cancels n to the d. That's gone. B to the log base b of a to the log base b of n. B to the log base b of n is n. Right? So let's just write this down. This is equal to now c times a over b to the d times, so this is, so a over b to the d times n to the log base b of a minus 1 over a over b to the d minus 1. And here there are going to be two cases. One case is that log base b of a is positive. Okay. So what does that mean? Basically, oh, no, sorry. Is this what I want to say? A over b to the d is less than 1. Okay, so good. So one case is going to be that, let's say, a over b to the d is less than 1. Oh, I hear a lot. Any questions? Oh, is there too much math here? Yeah. What? Is this better? No, it's off. Did my battery die? I think the battery just died. That's unfortunate. Okay. I'll just speak a little bit louder. Do you hear me, though, on the recorder? You hear me. So I guess for the webcast, it's going to work. But the room mic, unfortunately, seems to have died for some reason. I'll just yell. Let's see how good I am at yelling. Can you hear me in the back? Okay, so let's all just try to be a little bit quieter than usual, just so that the people in the back can hear me. Right, so I guess there's been a lot of math so far, but question? Why is it b to the d? Are you talking about right here?
Well, yeah, like,
and even there? Oh, okay. Right, so the point is, the point is that the work to, once you do the recursive calls, the work to combine them is proportional to n to the d, right? So at the root level, what is n? N is n, right? One level deeper, remember you divide it into parts where each part has size n over b. So the time it takes to combine them is n over b to the d. So b also gets raised to the dth power, right? And two levels down, the size of n is n over b squared. So now it gets raised to the d. So that's why you have b squared to the d, which is the same as b to the d squared. So, okay. Okay. Any other questions? Yeah.
how did you get n log b of a at the end, like the bottom?
N log base b of a? I used the trick. So what I said was a to the log base b of n is the same thing as b to the log base b of a, right? This is also known as a, raised to the log base b of n, which is equal to, again now, a to the b to the c is the same thing as a to the bc, which is the same thing as a to the c to the b, right? So I can write this as b to the log base b of n to the log base b of a, right? Which is n to the log base b of a. Okay? Any other questions? Yeah. This minus 1? This minus 1? Minus 1. You're saying I made a mistake there? I see. So I guess, yeah, this doesn't quite just cancel that. Is that what you're saying? because there's a minus 1 out here too. That's right. So actually, okay, so I can write this. Let's see. So I can write this as n to the d over n to the d. Yeah, good. Let's just do a little quick fix. 1 is the same thing as n over d to the n over d. So this is n to the d, that's n to the d, that's n to the d. So that also cancels. So this is n to the d. Okay, good. Yes, thank you. And that's important. That's important because now there are 2 cases. 2 more cases. So we already took care of the case that A is equal to b to the d. The 2 other natural cases are A is less than b to the d and A is bigger than b to the d. Right? So basically, let's try to compare. What I'm interested in knowing is comparing these exponents. Kind of which one is the bigger term? Is n to the d the bigger term, or is log base b of a the bigger term? Right? So case 1 is that d is bigger than log base b of a. Which if I raise both sides, if I do b to both sides, this is the same thing as saying b to the d is bigger than a. Right? So I had that a equals b to the d. Now I have a is less than b to the d. Right? If this happens, so right, this is also the same thing as saying a over b to the d is less than 1. Right? A over b to the d is less than 1. So the denominator is a negative number. And also the numerator is, if you think of n being large, since n to the d dominates, the numerator is also a negative number. So let me just kind of let me just multiply both the denominator and numerator by negative 1. So that means that my time, or my recurrence, is basically the same thing. It's up some constant times n to the d minus whatever over 1 minus whatever. This is some constant less than 1. This is something much less than n to the d. This is big O of n to the d. So that's when a is less than b to the d. Then I get O of n to the d. And the other case is when a is greater than b to the d. If a is greater than b to the d, this term dominates the n to the d. And then what I get there is O of n to the log base b of a, if a is bigger than b to the d. Does that make sense? So there, yeah.
You're basically done over there. I can just say in the other case it's O of n to the log a base b plus O of n to the d, and then put the numbers in there to show it dominates.
Right. So okay, just to repeat what you said, you could also just merge these into one case and say it's O of n to the d plus n to the log base b of a. You could also say that. I guess that's a kind of a way to compress this, but then, I mean, usually when you use these things, at the end of the day, you quickly want to know, like, what's the dominant term. So this tells you basically what the dominant term is going to be. Okay? So basically, there are 3 cases. A is equal to b to the d, a is less than b to the d, and a is greater than b to the d. And this thing, by the way, is called the master theorem. Right? The master theorem says when you have a recurrence that looks like this is the answer. There are 3 cases. So this is a good theorem to know for, well, analyzing lots of divide and conquer problems because it gives you the answer right away. As soon as you write down the recurrence, you know the answer. You just plug it into the master theorem. I don't have that much time left. In the last 5 minutes, I'll introduce you to another divide and conquer problem that has kind of a magical solution. We'll finish it on Tuesday and then do a little more divide and conquer on Tuesday. Which is matrix multiplication. Right? So matrix multiplication, sorry, just I ask you to be a little quieter than usual since I don't have a working mic, so the people in the back can hear. And I'll keep trying to yell. Can you still hear me in the back? Yeah. Okay, good. So matrix multiplication, I'm going to look at square matrix multiplication. So we have a matrix A times a matrix B. The entries of A look like A11 up to A1n, N1 up to ANN, and then we have the B's as well, right? And again, when you want the product matrix, it's again going to be n by n. And the way that you get the ijth entry, let's say this is Cij, is you take the ith row of A, you take the bth column of B, the jth column of B, and you take the dot product. And that gives you Cij. That's the definition of matrix multiplication, right? So the naive algorithm, kind of the straightforward one, is, first of all, initialize C to all zeros. And then you say, for I equals 1 to n, for j equals 1 to n, Cij plus equals AI, or I need one more loop. So now I want the dot product of the ith row with the jth column. So I'm going to basically loop over going right here and down here. So for k equals 1 to n, Cij plus equals Aik times Bkj. Sorry, I know I switched from upper to lowercase. These are little b's and little a's. Okay? So this is an n-cubed algorithm, right? N time in this loop, and each one of those times I'm in the loop, n more here, another n here. This is O of n cubed time. And we're out of time. What we're going to see at the beginning of next lecture is that we're going to basically do something like this. I'll just give you a sneak preview. Here's A, here's B. I'm going to break it up into 2 by 2 submatrices, or submatrices which are n over 2 by n over 2. And then I'm going to be able to write C as products and combinations of these multiplications. And we're going to do something clever, sort of like Karatsuba, to save a multiplication and do better. Okay? So that's coming Tuesday.